From childhood, we grow up believing that weight is something objects possess the way they possess color or shape. Rocks are heavy, feathers are light, planets are massive, and our bodies feel anchored to the ground by an invisible pull that seems permanent and unmistakable. Yet this sense that weight is a built-in property is not what physics reveals. The story of weight begins not with force, but with human experience. When you lift a suitcase from the floor, you feel strain in your muscles and an unmistakable resistance pressing back against your hands. When an elevator begins to rise, you notice a momentary heaviness as the floor pushes upward on your feet. These sensations are vivid and immediate, and so we accept them as the very definition of what weight must be. But sensation does not define reality. It only describes how our bodies interpret the world. Our nervous systems evolved to detect changes in position, tension in muscles, and pressure on the skin. None of these signals measure gravity directly. They measure the way our bodies resist movement or strain when something prevents us from falling freely. Without that resistance, the feeling of weight disappears, even when gravity has not changed at all. Astronauts orbiting Earth live in a constant gravitational field, only slightly weaker than that at the surface, yet they experience continuous weightlessness. This alone hints at a deeper truth. What we instinctively treat as an object's weight arises not from gravity acting on it, but from something else entirely. It arises from the interaction between the body and the surface that supports it. To understand why this distinction matters, we must first consider what physics means by mass. Mass is not heaviness. It is not a measure of how difficult something is to carry. In physics, mass represents how much an object resists acceleration and how strongly it influences other masses through gravity. Mass does not change whether you are on Earth, on the Moon, or drifting in interplanetary space. Your mass is the same in every environment. But your weight changes dramatically from place to place because weight is not a property of the object. It is a relationship between the object and its surroundings. Early scientists recognized that objects do not fall because of their shape or color or composition, but because they experience the same gravitational acceleration regardless of their mass. Remove air resistance and a hammer and a feather fall side by side, as demonstrated during an Apollo mission when astronauts carried out a simple but powerful experiment on the lunar surface. In the vacuum of the Moon, both objects struck the ground together, just as Galileo predicted centuries earlier. Their masses were wildly different, but their acceleration toward the surface was identical. This experiment makes clear that weight, as we feel it, cannot simply be gravity acting downward. If gravity alone determined weight, objects of different mass then would fall differently. Yet they do not. Because of experiments like these, physics defines weight not as a universal downward force, but as the force a surface exerts upward on an object to keep it from accelerating freely. Step onto a bathroom scale, and you are not measuring how strongly Earth pulls on you. You are measuring how strongly the scale pushes back on your feet to prevent you from falling through it. In other words, the scale measures the resistance to your natural motion, not the gravitational field itself. If you were falling in a vacuum with the scale beneath your feet, the scale would read 0, even though Earth's gravity is acting on you throughout the fall. This reveals a profound mismatch between our intuition and the physical truth. The idea that weight is conditional rather than absolute is surprisingly difficult to accept. We feel weight constantly and therefore assume it must be a fixed characteristic. Yet the moment frictionless free fall removes the support force, the sensation of weight vanishes. This is why roller coasters create moments of apparent floating. As the car crests a hill and accelerates downward, your body follows a path close to the natural free fall trajectory. The seat pushes on you less, and you feel lighter. The track has not changed Earth's gravity. It has only changed how much the seat must resist your motion. What you are feeling is not gravity becoming weaker, it is support becoming weaker. Understanding this difference prepares us for a deeper conceptual shift. When we talk about an object's weight, we are really speaking about what happens when its natural motion is interrupted. If nothing interrupts it, if nothing pushes up against it or holds it still, then it follows a gravitational path that is built into the geometry of space-time itself. This means weight is never something an object carries with it. It is something that arises only when the object is prevented from moving freely. This realization marks the first step towards seeing gravity not as a simple force, but as a more subtle and elegant phenomenon. What makes this transformation in understanding so important is that it allows us to separate our sensory experience from the underlying physics. We evolved to feel weight because it helped our ancestors navigate cliffs, lift food, and judge balance. Our senses report pressure, tension, and resistance, not the curvature of space-time. They tell us what happens at the surface of our feet or hands, not what happens to our trajectory through the universe. Physics, on the other hand, demands that we distinguish the signal from the sensation and that we define weight with precision rather than intuition. This is the foundation on which everything else in this story will rest. As soon as we separate weight from mass and sensation from definition, the mysteries of gravity begin to unfold in unexpected ways. The world becomes stranger and more revealing. We learn that our everyday language conceals deeper truths and that our bodies, reliable though they may seem, are not perfect instruments for understanding the structure of nature. Physics invites us to go beyond perception and into explanation. And yet, even with this clarity, a question remains. If weight is not simply the downward pull of gravity, but the upward push of a surface preventing natural motion, what is gravity actually doing? What is the mechanism that shapes the motion of planets, drops objects toward the ground, and guides the path of light itself? The answer to this question does not begin with Einstein, as one might expect, but with an earlier framework that transformed the human understanding of motion and force. As our narration moves forward, we will step into the world of Isaac Newton, where gravity was first unified into a single universal principle. Weight feels absolute, but physics shows that it is conditional. To understand this mismatch between experience and reality, we must revisit the first revolutionary framework that explained gravity. What Newton accomplished was nothing short of astonishing. Before his work, gravity was seen as a familiar but mysterious tendency of things to fall downward. There was no unifying idea linking the apple that drops from a tree to the path traced by the moon in the sky. Newton changed that with a single insight. He recognized that the same rule that governs the motion of celestial bodies also governs the motion of objects on Earth. In his view, gravity was a universal force, acting between all masses across all distances, predictable through clear mathematical relationships. It was the first time a single principle connected the heavens with the ground beneath our feet. This connection was built upon careful observation. When an object falls freely, it accelerates in a way that is measurable and predictable. Newton drew on earlier studies and extended them into a universal law that explained why planets move in nearly elliptical paths and why objects fall at a constant acceleration near the surface. His law of universal gravitation stated that any two masses attract each other with a force that depends on their masses and how far apart they are. This was not a guess, but a model built from data. It described the motion of planets, the tides of the oceans, and the behavior of falling bodies with remarkable precision. For the first time, gravity became a quantifiable interaction. But even as Newton offered this profound unification, he recognized that something was missing. He could describe what gravity did, but he could not explain why it acted the way it did. In his framework, gravity seemed to act instantly across space, binding stars and planets in a cosmic dance without any delay. The idea that influence could travel instantly raised deep questions. How could one mass reach out across empty space and tug on another without any mediating substance or signal? This puzzle lingered for centuries and would only be resolved much later. For now, though, Newtonian gravity served as the most precise tool available for calculating weight. With Newton's laws, physics gained a reliable way to calculate the force that a planet's surface must exert to support an object resting on it. The local gravitational acceleration determines how much upward force the surface must provide, and that upward force is what we measure as weight. Under this framework, weight seemed like a straightforward concept. Yet even here, subtle complexities remained. The force of gravity is not uniform across Earth. It varies with latitude, altitude, and geological structure. These variations are small but measurable, revealing that even in a Newtonian world, weight is not fixed or absolute. It depends on where you are and how you are moving. Early scientists also conducted precise measurements to determine the gravitational constant, a value that expresses how strong gravity is in general. These experiments were extraordinarily delicate. They involved measuring tiny deflections of suspended masses and required careful isolation from vibrations and environmental influences. The fact that these tiny effects could be measured at all demonstrates how thoroughly physics seeks reliable evidence. From these measurements came the ability to calculate the gravitational force between any two masses. Yet even as the numbers became more precise, the conceptual problem remained. Gravity still appeared as an unexplained influence, a force that operated without a clear mechanism. This uncertainty encouraged deeper thinking about the difference between mass and weight. Mass is a measure of inertia, of how strongly an object resists changes in motion. It is the same everywhere, whether on Earth or drifting in the space between planets. Weight, however, is the interaction between mass and the gravitational environment. A person standing on the surface of Earth might feel a strong weight, while the same person floating freely in orbit feels none at all. Their mass has not changed, but the supporting surface that once provided resistance is gone. The physical distinction between mass and weight became clearer. The perceptual distinction remained just as confusing as ever. Newton himself hinted at this complexity when he considered what would happen if an object were falling freely. In that state, no surface pushes against the object, and therefore the object experiences no weight. This idea is the seed of a much later insight, the idea that free fall is a kind of natural motion that reveals something fundamental about gravity. But at the time, the concept was not pursued deeply. It remained an interesting observation rather than a transformational idea. The physics community would continue using weight as a straightforward measure of gravitational pull, even though that definition did not fully capture what the body actually experiences. Meanwhile, human perception continued to reinforce the mistaken idea that weight is an inherent feature of objects. Everyday life offers countless examples that seem to confirm this illusion. Rocks remain heavy, whether held in a hand or set upon the ground. Watermelons feel heavy as you lift them from a table. Suitcases strain your arms no matter how you position them. None of these sensations reveal the actual physics at work. They only report the muscular effort required to counteract gravity through contact forces. The sense of heaviness is not a direct measure of gravitational attraction. It is a measure of resistance. The body reports tension and compression, not the gravitational field itself. In truth, the gravitational field acts continuously whether or not you feel anything at all. Remove the supporting surface, and the sensation disappears. This was demonstrated dramatically by astronauts aboard the International Space Station. They drift weightlessly in an environment where Earth's gravity is still strong. Their bodies are in a perpetual state of freefall, following a curved path around the planet. The space station itself falls at the same rate, creating a situation in which the astronauts experience no supporting force. They are not outside gravity, but within it, moving in harmony with it. Every moment of floating in orbit illustrates that weight is not a built-in property of mass, but a result of being held up against the natural motion defined by gravity. This realization, though simple, marks a profound turning point. It forces us to separate the feeling of weight from the physical definition of weight. It reveals that what we sense is not gravity directly, but the interruption of our natural path through space-time. Newton offered a powerful description of how gravity influences motion, but even he did not answer the fundamental question. What is gravity itself? Why does it act the way it does? What shapes the path of planets and the falling motion of objects? To answer these questions, physics would have to move beyond forces entirely and redefine gravity not as a pull, but as something woven into the structure of the universe. To reach that deeper understanding, we move next into the world of Einstein, where space and time blend into a single fabric, and the familiar concept of force gives way to a new geometric vision. The step from Newton to Einstein is not a replacement, but an expansion, a shift from describing motion to explaining the shape of motion itself. As our exploration continues, we begin to see that weight is not only conditional, but perspectival. And the key to unlocking this truth lies in reframing gravity from a force to a property of space-time. The transition from Newton's world to Einstein's begins with a simple question that puzzled scientists for centuries. Why do all objects fall with the same acceleration, regardless of their mass? Under Newtonian physics, gravity is a force that depends on mass. If that force depends on mass, and the response to force also depends on mass, then the two relationships cancel out. Heavy and light objects accelerate identically. This mathematical coincidence was known, accepted, and used, but it did not offer any deeper understanding. It simply worked. Einstein approached the puzzle from a fresh direction. He treated this equality not as a coincidence, but as a clue. He asked what it would mean if falling freely were not just a motion caused by gravity, but the natural motion of objects in the absence of any force. The thought experiment that guided him was remarkably simple. Imagine a person falling from a great height inside a sealed room. During the fall, the person would float effortlessly, objects would hover, and nothing inside the room would reveal that gravity exists. The person would feel weightless as surely as an astronaut in orbit. This state of weightlessness is not created by a lack of gravity, but by the lack of any surface pushing upward. In this situation, all parts of the room and everything inside it accelerate together. There is no internal resistance, and thus no weight. Einstein realized that this feeling was not a trick of perception, but a profound insight into the nature of motion. The idea that falling freely is indistinguishable from floating in the absence of gravity became the seed of the equivalence principle. This principle states that gravity and acceleration can mimic each other so completely that, in a small enough region of space, one cannot tell the difference. If a person stands inside a windowless rocket, accelerating upward in deep space, they feel a force pressing their feet to the floor, exactly as they do when standing on Earth. If the rocket stops accelerating, the sensation vanishes. In the same way, standing on Earth creates the sensation of weight, because the ground resists the natural motion that gravity dictates. Einstein saw that the experience of weight was telling us something fundamental. It was not measuring gravity, it was measuring the interruption of free fall. This insight marks the point where intuition begins to diverge sharply from the physical truth. We grow up believing that weight is a product of gravity pulling downward. In fact, what we feel is the upward push of whatever supports us. Gravity itself is not felt directly. What we experience as heaviness is the surface acting on us, forcing us away from the path we would naturally follow. This distinction, though subtle, transforms the meaning of weight entirely. It is no longer an inherent feature of matter or a simple consequence of gravitational pull. It becomes a reaction force, a response to being kept still when nature attempts to move us. Understanding this requires revisiting how objects behave when nothing interferes with their motion. If an object floats freely far from any massive body, it follows a straight line through space-time. If it moves toward Earth under the influence of gravity, it follows a curved path. But this motion is still natural in the sense that no Force is acting on it in the traditional Newtonian meaning. Gravity is not pushing or pulling. It is guiding the object along a trajectory shaped by space-time itself. In this view, weight appears only when something obstructs this path. When you stand on the ground, the solidity beneath your feet prevents you from following the downward curve that space-time dictates. The ground pushes upward, and that push is what you feel. The more deeply scientists examine this idea, the more they realize that weight is not only conditional, but entirely frame-dependent. An astronaut floating in orbit feels weightless, even though Earth's gravity is strong. A person in an accelerating spacecraft feels weight even though no gravitational field is present. A falling object feels nothing even though gravity acts upon it. These examples reveal a pattern. Weight does not measure gravity, it measures the deviation from free fall. This realization prepares the way for Einstein's next leap, the recognition that gravity is not a force, but the curvature of space-time itself. Before exploring that geometric perspective, it is important to appreciate how fully this shift redefines our understanding. The idea that gravity curves space-time will soon reshape every familiar notion about motion, energy, and the structure of the universe. But the story begins here, with the recognition that weight is not a reliable guide to what gravity is. Weight is a sensation shaped by biology and a quantity defined by physics, but it does not reveal the nature of gravity directly. To follow that path, we must look beyond what our bodies feel and examine how objects move when no force interferes. Everything we have discussed so far leads us to a single conclusion. Weight is not a universal property, but a conditional experience. It arises only when an object is prevented from moving freely in the gravitational field around it. It depends on support, on motion, and on frame of reference. This is why physics distinguishes mass, which is intrinsic, from weight, which is relational. Mass describes what an object is. Weight describes what happens when that object interacts with its surroundings. Our senses blur the difference because they evolved to detect forces on the body, not the geometry of space-time. Physics separates them with precision. At this stage in the story, we have built the foundation necessary for the transformation that lies ahead. Newton revealed the universal reach of gravity and gave us tools to calculate motion and force. But Newton's vision remained incomplete. It treated gravity as a mysterious influence that acted instantaneously across space. It did not account for the geometry of the universe or the fact that free fall resembles the absence of force. To resolve these puzzles, physics needed a new idea, one that would unify mass, motion, and geometry into a single picture. That idea emerges in the early 20th century with Einstein, who recast gravity not as a pull but as the natural motion of objects through curved space-time. When we step into that framework in the next chapter, weight will appear not as an attribute of matter, but as a reaction to resisting the shape of space-time. With this perspective in place, the mystery deepens and the journey into gravity's true nature begins. For centuries before Newton, gravity was treated as a familiar but unexplained fact of the world. Stones fell, rain descended, and planets traced elegant paths through the night sky. Yet no single idea connected these motions into one coherent picture. People observed falling objects every day, but no one could say what governed their behavior with mathematical certainty. The celestial realm seemed even more mysterious. The wandering planets, moving in long arcs across the heavens, obeyed patterns that astronomers could describe but not fully explain. Into this landscape of partial understanding stepped a mind willing to imagine that the forces shaping the universe could be described by the same rules that applied to objects on Earth. Newton did more than offer new equations. He united the earthly and the cosmic into a single framework governed by universal principles. His journey began with an idea so simple that it could be sketched in the sand. If a stone is thrown gently, it arcs through the air and falls. If it is thrown harder, it travels farther before striking the ground. If it could be thrown with enough speed, the curvature of Earth would cause the ground to fall away beneath it, at the same rate that the stone falls toward the planet. The stone would never land. It would circle the planet endlessly. This imaginary scenario revealed a profound truth. The motion of a falling stone and the motion of the moon differ not in essence but only in scale and speed. In both cases, Earth's gravity shapes the path. One object falls and strikes the ground. The other falls forever but continually misses. Gravity is the common thread. From this insight, Newton developed the law of universal gravitation. He proposed that every mass in the universe attracts every other mass with a force whose strength depends on their masses and their distance from each other. This force decreases with the square of the distance, a relationship drawn from meticulous astronomical observations. It explained why planets trace nearly elliptical orbits, why comets travel in long stretched paths, and why tides rise and fall in rhythm with the positions of the moon and the sun. It also provided a way to calculate the gravitational force between any two objects, no matter how large or small. The universe became consistent and predictable under this new law. Newton's equations were not only elegant, they were astonishingly accurate. But the implications of this law extended beyond celestial mechanics. It also defined weight in a way that seemed straightforward. The gravitational force between Earth and an object on its surface determines the downward pull that must be countered by the ground or by any supporting surface. This upward push, equal in magnitude to the gravitational pull, is what physics labels weight. Using the value of Earth's gravitational acceleration, scientists could calculate the weight of any object from its mass. The relationship seemed clean and absolute. Yet even here, subtle variations existed. Because Earth bulges slightly at the equator and flattens at the poles, the gravitational field is not the same everywhere. People weigh slightly more at the poles than at the equator. They weigh slightly less atop mountains than at sea level. In Newton's world, weight depended on location even before Einstein revealed deeper complexities. To measure gravity in absolute terms, scientists needed to determine the gravitational constant. This experiment required extraordinary sensitivity. Masses suspended in delicate balance would twist imperceptibly due to their tiny mutual attraction. The deflection was so small that only a careful observer in a quiet environment could detect it. From these subtle motions came a precise value that allowed the gravitational force to be calculated anywhere in the universe. The ability to measure such a faint effect demonstrated the rigor with which physics operates. Gravity was no longer a vague idea. It became a quantifiable interaction, governed by a constant woven into the fabric of the cosmos. Yet even as Newton's achievements brought unprecedented clarity, they also highlighted questions that remained unanswered. His law treated gravity as a force that acts instantly across any distance. If the sun were to disappear suddenly, Newton's equations implied that Earth would feel the change immediately, but nothing else in physics acted this way. Every other influence seemed to propagate through space at a finite speed. Light, sound, and electromagnetic waves all took time to travel. Why would gravity be different? Newton himself acknowledged this discomfort, noting that he did not pretend to describe the mechanism of gravity. He only described how it behaved. The theory worked, but it did not explain the underlying cause. Despite this limitation, Newton's framework dominated scientific thought for centuries because it worked so well. It predicted eclipses with extraordinary precision. It guided the paths of spacecraft. It described the rise and fall of tides and the motion of planets with near-perfect accuracy. Even today, engineers use Newtonian calculations to plan rocket trajectories and satellite orbits because at most scales the predictions are indistinguishable from those of general relativity. But in a few rare cases, discrepancies appeared. The orbit of Mercury, for example, precessed slightly faster than Newton's law predicted. This deviation was tiny but measurable, and no amount of refinement in calculation could resolve it. Newton's model, though powerful, left small but persistent cracks. These cracks hinted that gravity might be more than a force transmitted through space. They suggested that something deeper shaped motion, something that Newton's equations described but did not reveal. The difficulty of explaining the mechanism behind gravity and the anomalies observed in planetary motion pointed toward an idea that required a new way of thinking. It would take centuries and a mind capable of reimagining space and time themselves to address these questions. That mind belonged to Einstein, who saw that the equality of gravitational and inertial mass was not a mathematical convenience, but a gateway to a different understanding of gravity altogether. But before we cross that threshold, it is worth appreciating what Newton accomplished. He unified the motions of the heavens and the motions of the earth. He provided a way to calculate weight with precision. He transformed gravity from a mystery into a universal interaction governed by simple mathematical rules. His framework was a triumph of human thought, yet it was incomplete. It could describe gravity, but not explain its nature. The next step would require reshaping the very stage on which all motion unfolds. As we move forward, we leave behind the world where gravity acts as a force transmitted across empty space. We enter a realm where gravity is expressed not through invisible pulls, but through the geometry of space-time. The shift from Newton to Einstein is more than a refinement. It is a transformation. Newton described the effects of gravity. Einstein revealed its essence. In the centuries following Newton's work, scientists applied his laws with growing confidence. Observatories refined measurements of planetary motion, revealing patterns so consistent that they seemed like signatures of a clockwork universe. Every planet, every moon, and every comet followed paths that could be predicted with Newtonian equations. Sailors relied on celestial mechanics to navigate across vast oceans. Astronomers calculated the return of comets with remarkable accuracy. Even the discovery of new planets emerged from this framework. When Uranus drifted from its expected orbit, scientists reasoned that an unseen planet must be tugging on it. Using Newton's equations, they predicted where this hidden world should be found, and Neptune was soon observed exactly where the calculations indicated. It was a triumph, not just of mathematics, but of a worldview that suggested nature's behavior could be understood through universal laws. Yet behind this success lingered a conceptual tension. Newton's theory worked beautifully in practice, but did not explain how gravity operated. According to the law of universal gravitation, Earth pulls on the Moon, the Sun pulls on Earth, and every star pulls on every other, all of it occurring instantly across enormous distances. But what carried this influence? How did one mass communicate its presence to another? Newton himself expressed discomfort with the idea of action at a distance. He envisioned no physical mechanism by which gravity could transmit its effects. Instead, he offered a description that matched observation, leaving the underlying cause open. Science accepted this incompleteness because no better alternative existed at the time, and the theory was extraordinarily accurate. Even so, certain phenomena expose the edges of Newtonian thinking. One of the most intriguing involved the orbit of Mercury. For generations, astronomers measured Mercury's path around the Sun and found a tiny discrepancy between observation and Newtonian prediction. Mercury's elliptical orbit slowly rotated or precessed over time. Most of this precession was understood. The gravitational pull of other planets, particularly Jupiter and Venus, perturbed Mercury's orbit. Once these influences were calculated, almost all of the precession could be explained. Almost, but not entirely. A small remainder remained stubbornly unaccounted for. Some scientists proposed that an unseen planet inside Mercury's orbit might be responsible. They even gave this hypothetical world a name. But years passed, and no such planet was ever found. The unexplained precession persisted, suggesting that Newton's description of gravity might be incomplete. Meanwhile, the question of gravitational propagation remained unresolved. If the Sun were suddenly removed from the universe, Newtonian physics implied that Earth's orbit would instantly change direction. Yet, the study of electromagnetism showed that no influence could travel faster than light. If light required time to cross the distance from the Sun to Earth, shouldn't gravity also require time? The idea that gravity acted instantaneously across space seemed inconsistent with emerging insights into the nature of forces. Scientists recognized this inconsistency, but lacked a framework to address it. The classical picture was powerful, but it was not final. Despite these conceptual challenges, Newton's theory remained central to scientific progress. Engineers planning the paths of early spacecraft relied on Newtonian calculations because they were simple and sufficiently precise for most practical purposes. Astronomers used the theory to predict eclipses, understand the behavior of binary star systems, and analyze the motion of celestial bodies across the galaxy. Newton's equations were woven deeply into the fabric of physics, from classroom instruction to advanced research. They served not only as a tool for calculation, but as a guide for intuition. Gravity felt like a force, and Newton's framework made that force comprehensible. But intuition, as we have already seen, is not always the best path to truth. As physicists studied motion more carefully, they noticed that objects in free fall behaved as though gravity did not act on them at all. A freely falling object experiences no internal forces. It feels weightless, regardless of its environment. In Newtonian physics, this made sense mathematically, but raised deeper questions about what the experience of weight really meant. If gravity acts on an object, why would that object feel nothing while falling? This puzzle would later become the foundation of a revolutionary insight, but even in Newton's time, it hinted at something subtle. The feeling of weight did not match the presence of gravitational force. The two were related but not identical. Meanwhile, the study of tides provided another window into the behavior of gravity. Tides occur because the Moon pulls slightly more strongly on the side of Earth closest to it and slightly less strongly on the far side. This difference stretches Earth's oceans, creating the familiar rise and fall of water levels along coastlines. Newton's theory explained this perfectly, showing that gravity acts at a distance and varies with separation. But the existence of tides also underscored the conceptual challenge of action at a distance. The Moon's influence was real and measurable, yet nothing visible connected the two bodies. If gravity was a force, it acted in a way unlike any other known phenomenon. Despite all these challenges, Newton's description remained the best available. It transformed physics by linking terrestrial and celestial motion into one system. It revealed that the same mathematical law governs falling apples and planetary orbits. It enabled predictions of extraordinary accuracy and guided scientific thinking for centuries. Yet its power highlighted its limits. It described what gravity did, but not why it did it. It provided tools for calculating weight, but not for explaining the origin of weight as an experience. It offered equations, but not a mechanism. By the late 19th century, scientists recognized that something deeper must lie beneath Newton's model. The failure to explain Mercury's precession, the conflict with the finite speed of information, and the peculiar nature of free fall, all signaled that gravity might not be a traditional force at all. These clues built pressure for a new idea, one that would require reimagining space and time themselves. When Einstein entered the scene, he approached gravity not as a problem of forces, but as a problem of geometry. His insight would reshape physics entirely. Before we arrive at that new vision, we pause to appreciate the brilliance and the limitations of the Newtonian world. Newton gave humanity a universal framework for predicting motion and for calculating weight. But he left unanswered the question of gravity's true nature. That question now guides us into the next chapter, where Einstein will dissolve the idea of gravity as a force and replace it with a curvature that shapes the universe itself. As the 19th century drew to a close, the confidence in Newton's universe began to rest on increasingly fragile ground. The theory still worked beautifully across most familiar situations, yet subtle discrepancies and deeper conceptual questions continued to accumulate. Scientists had long accepted that Newton's equations described gravity with extraordinary precision, but many sensed that the theory did not yet reveal the full story. It described the effects of gravity, but did not illuminate its origin. It explained how bodies moved, but not what shaped the paths they followed. The fact that gravity appeared to act without any medium, instantly and across vast distances, felt strangely at odds with the growing understanding that all interactions must propagate through space with some finite speed. The completeness of Newton's world was beginning to unravel, not because it failed dramatically, but because it succeeded in ways that revealed its own incompleteness. One of the most striking examples of this incompleteness came from the study of light. Experiments showed that the speed of light was constant for all observers, regardless of their motion. This discovery challenged the foundations of classical physics. In Newton's world, time and space were absolute, providing a fixed backdrop against which all events occurred. But the speed of light refused to adjust itself to the motion of the observer, suggesting that either light behaved in a unique and inexplicable manner, or that the familiar notions of time and space themselves needed to be reconsidered. This inconsistency cast new shadows over the Newtonian picture of gravity. If the structure of space and time was not absolute, how could a force operate within it in the instantaneous way that Newtonian theory required? As researchers considered these puzzles, they kept returning to the equality of inertial mass and gravitational mass. Inertial mass is the measure of how strongly an object resists acceleration. Gravitational mass is the measure of how strongly it interacts gravitationally with other masses. Newton's equations depend on these two quantities being identical. If they were not, heavy and light objects would not fall at the same rate. For centuries, this equality was treated as a curious but necessary coincidence. Yet it hinted at a deeper unity between inertia and gravity, a unity that Newton himself could not explore fully. The equality did not arise naturally within the Newtonian framework. It simply existed because nature demanded it. This unexplained symmetry would later become a doorway through which Einstein would step into an entirely new conception of gravity. Meanwhile, increasingly precise measurements of planetary orbits continue to reveal small deviations from Newtonian predictions. Mercury's orbit remained the most famous example, but it was not the only one. Other subtle anomalies began to appear as telescopes improved and as mathematical methods became more refined. Although these deviations were tiny, their persistence suggested that the Newtonian picture, while powerful, might not be the final word. The laws worked within the limits of measurement, but as measurement improved, the edges of the theory were exposed. This is often how physics progresses. The precision that confirms a theory eventually becomes the tool that reveals its limitations. The question of gravitational propagation also began to trouble physicists more deeply. If the sun's influence on Earth were truly instantaneous, then gravity operated outside the rules that governed every other known interaction. This seemed unlikely. More importantly, it suggested that gravity might not be a force in the traditional sense. Forces such as electromagnetism propagate through fields that fill space and transmit influence at finite speeds. If gravity acted differently, what made it unique? Was it an exception to the natural order, or was the understanding of gravity incomplete? These questions pressed on the minds of scientists who were beginning to suspect that a deeper structure underlay the familiar equations. Into this growing uncertainty came a new way of thinking about motion itself. Physicists began to explore the idea that space and time might be interconnected rather than separate. If the fabric of the universe could change depending on the motion of the observer, then perhaps gravity did not act within space and time, but instead shaped them. This idea was not yet fully formed, but the seeds had been planted. Newton's laws assumed a rigid stage on which the actors moved. But what if the stage could bend, stretch, or curve? What if gravity was not a force acting on objects, but a feature of the stage itself? These philosophical questions were not mere abstractions. They were driven by the need to explain real and measurable phenomena that no existing theory could fully reconcile. They created a sense of anticipation in the scientific world, a feeling that the next great step was approaching. And indeed it was. Einstein, guided by an ability to imagine physical scenarios with astonishing clarity, took up the challenge. He asked what it would mean if free fall were not a response to gravity, but the natural motion of objects in the absence of force. He asked what it would mean if the geometry of the universe dictated the paths that objects follow. He asked how motion would appear if time itself could change depending on the observer. Before these insights could transform physics, there was one more conceptual shift that needed to occur. Scientists had to recognize that the experience of weight did not originate in gravity directly. It arose from something resisting the motion that gravity dictates. This distinction opened the path to a new understanding of gravity as something woven into space-time itself. It set the stage for Einstein's recognition that gravity is not transmitted through empty space, but is expressed in the curvature of that space. The familiar sensations of heaviness, the predictable fall of objects, and the paths of planets all arise from the shape of the universe rather than from a force acting across it. And so the story reaches a turning point. Newton's framework, brilliant though it is, cannot carry us further. It describes gravity, but cannot explain its essence. It predicts weight, but cannot explain why weight disappears in free fall. It unifies celestial and terrestrial motion, but cannot reconcile the speed of light or the structure of space-time. To move beyond these limits, we must step into Einstein's world, where gravity becomes geometry and where weight becomes a reaction to resisting natural motion. In the next chapter, we enter this new landscape. Einstein's insight will dissolve the image of gravity as a force and reveal a universe where falling freely is the clearest expression of nature's design. When Einstein began to question the nature of gravity, he did not start with complex mathematics or advanced theories. He began with an experience so familiar that most people never question it. He imagined what it would feel like to fall freely. This simple thought, so ordinary in everyday life, opened a doorway into a new understanding of the universe. While Newton described gravity as a force that pulls masses toward one another, Einstein wondered whether this pull was truly a force at all. He asked whether the experience of falling might reveal something deeper about the structure of nature. If a person inside a small closed room dropped toward Earth, the person would float as though gravity had vanished entirely. Objects released inside the room would hover weightlessly. The person would feel no pressure beneath their feet, no strain in their muscles, no sensation of being pulled anywhere. Einstein recognized something extraordinary in this simple scenario. He understood that the feeling of being weightless during free fall was not an illusion, but a clue. This was the beginning of what Einstein called his happiest thought. If a person cannot distinguish falling freely in a gravitational field from floating far away from any massive body, then perhaps these two experiences are physically identical. Perhaps the absence of weight in both situations reveals the underlying truth that gravity itself is not a force acting on objects. Instead, objects in free fall follow natural paths, paths determined not by force, but by the shape of space-time. This idea was revolutionary because it suggested that free fall is not a condition to be explained by gravity. It is gravity. The weight we feel when standing on a surface arises not from being pulled downward, but from being pushed upward by the ground, which interrupts our natural motion through space-time. To explore this idea further, Einstein considered the opposite scenario. What if a person stood inside a rocket that accelerated upward in deep space, far from any gravitational influence? The floor would press against the person's feet with a steady force. If the acceleration matched Earth's gravitational acceleration, the person would feel exactly the same as they do while standing still on Earth. There would be no experiment the person could perform inside the rocket to determine whether the force came from gravity or from acceleration. This equivalence between acceleration and gravity suggested that they were two manifestations of a single underlying principle. Einstein began to see that gravity might not be a force transmitted across space, but a reflection of how objects move in a curved geometry. This insight became the equivalence principle, one of the foundational ideas of general relativity. It states that locally, meaning in a small enough region of space, the effects of gravity cannot be distinguished from the effects of acceleration. This principle is not a guess. It arises from the observed fact that all objects fall with the same acceleration regardless of their mass or composition. If gravity acted like other forces, different objects might respond differently. But because they do not, a deeper explanation must exist. Einstein realized that this universality could only be explained if gravity guides motion without exerting a traditional force. Objects follow paths that space-time itself prescribes. At this point, Einstein's thinking began to move beyond intuition and into the realm of geometry. He imagined space-time not as an empty backdrop, but as a dynamic fabric that could bend, stretch, and curve. A massive object like Earth or the Sun does not pull on smaller objects across a distance. Instead, it shapes the geometry around it. Smaller objects move along the straightest possible paths within that curved geometry. These paths, called geodesics, represent the natural motion of objects when no other forces act. This means that when you drop a stone, it is not being pulled downward, it is following a geodesic in curved space-time. When you stand on the ground prevents you from following this natural path. You feel weight not because gravity pushes you down, but because the surface pushes you up. This view also explained why astronauts orbiting Earth experience weightlessness. The gravitational field at the altitude of the International Space Station is still strong, only slightly weaker than at Earth's surface. But the astronauts and the station itself are following geodesics as they fall continuously around Earth. They are in free fall, and therefore they feel no support force. Weightlessness is not the absence of gravity, it is the absence of resistance. This distinction once again reinforces the idea that weight arises only when motion is constrained. Einstein's new framework required rethinking many familiar concepts, including time itself. Experiments showed that clocks in stronger gravitational fields run more slowly than clocks in weaker fields. This effect, known as gravitational time dilation, is a direct consequence of curved space-time. It has been measured in laboratories, observed in the timing of signals from satellites, and accounted for in the operation of the global positioning system. Without correcting for gravitational time dilation and the effects of relative motion, GPS would drift rapidly and become useless within hours. Einstein's theory is not abstract philosophy. It is a practical description of how the universe operates. Light itself also follows curved paths in the presence of gravity. During a solar eclipse in the early 20th century, astronomers measured the deflection of starlight as it passed near the Sun. The observed bending matched the predictions of general relativity, providing one of the earliest confirmations of Einstein's theory. Later observations, including more precise measurements using radio waves, confirmed the effect with increasing accuracy. Gravity does not pull on light. Light travels along geodesics, and when space-time curves, geodesics curve as well. General relativity also explained the long-standing puzzle of Mercury's orbit. The curvature of space-time near the Sun creates a small correction to the planet's motion, causing the orbit to precess slightly more than Newtonian physics predicts. This additional precession matches observation perfectly. It is not an added force, but a consequence of the geometry through which Mercury travels. This elegant explanation revealed the power of Einstein's idea. Problems that resisted explanation under Newton's model became natural results of curved space-time. Einstein had not replaced Newton's laws. He had expanded them, revealing that Newton's description works perfectly in situations where space-time curvature is gentle and speeds are far below the speed of light. But in strong gravitational fields, or at high speeds, the geometry of space-time cannot be ignored. Weight, force, and motion all arise from that geometry. This new perspective marks a turning point in our story. Gravity is no longer seen as an invisible pull. It becomes the shape of the universe itself. In the next part, this idea will deepen as we explore how free fall expresses the true nature of gravity and why weight is not a fundamental property, but a reaction to resisting the geometry of space-time. As Einstein continued developing his theory, he realized that the equivalence principle was more than a clever observation. It demanded a complete rethinking of how motion worked at the deepest level. If a freely falling observer experiences no gravitational force, then the laws of physics for that observer must resemble those of an observer drifting in empty space far from any massive body. This meant that gravity could not be treated as a traditional force that pushes or pulls. Instead, it must arise from something more fundamental, something that shapes the motion of all objects without acting on them directly. Einstein saw that the only way to satisfy this requirement was to allow space-time itself to become dynamic, able to bend and curve in response to mass and energy. This idea was radical because it transformed space-time from a passive stage into an active participant in the workings of the universe. In Newton's world, objects moved through a fixed, unchanging backdrop. In Einstein's world, the backdrop had structure. Mass and energy told space-time how to curve, and space-time told objects how to move. This interplay became the foundation of general relativity. The geometry of space-time replaced the concept of gravitational force. Objects no longer needed to be pulled toward one another. Instead, they followed the straightest possible paths through a curved geometry. The remarkable thing about this approach is that it preserves a simple truth about free fall. A falling object experiences no force. It simply moves naturally within the geometry that surrounds it. To visualize this, imagine a marble rolling across a smooth, curved surface. If the surface bends downward, the marble's path curves along with it. Nothing pushes or pulls on the marble. It merely follows the shape of the surface. In a similar way, Earth curves the space-time around it, and falling objects follow that curvature. This analogy is limited because space-time is not a surface in a literal sense, but it helps reveal how gravity emerges from geometry rather than force. What we traditionally thought of as gravitational pull becomes the natural motion of objects moving through a curved four-dimensional structure. This geometric picture allowed Einstein to explain the equality of inertial and gravitational mass in a way Newton never could. If gravity is not a force but a consequence of space-time geometry, then it must influence all objects in the same way, regardless of their mass or composition. A feather and a hammer fall at the same rate, not because a coincidence causes two different masses to respond identically to a force, but because space-time provides the same curvature for both. Their natural path is the same. Only forces that act on objects directly can distinguish between their masses. Gravity, which is not a force in this framework, does not. With this conceptual shift in place, Einstein constructed equations that describe how mass and energy determine the curvature of space-time. These equations, known as the field equations of general relativity, form the core of the theory. They are complex and elegant, tying together geometry, matter, and motion. But the deep meaning behind them can be understood without mathematics. The presence of mass and energy bends space-time. The bending of space-time guides the motion of objects. This simple statement captures the essence of gravity in Einstein's theory. From this perspective, weight becomes a subtle and layered concept. In everyday experience, weight feels like a downward pull. But in general relativity, weight is the sensation of being pushed upward by a surface that prevents you from following your natural geodesic path. When you stand on the ground, the solidity beneath your feet prevents you from moving along the curve that space-time dictates. The ground pushes upward, and your body interprets this upward push as weight. When you sit in a chair, the chair pushes upward. When you lie in bed, the mattress pushes upward. In all these cases, the sensation of weight emerges from resisting spacetime's guidance. In free fall, no resistance exists, so weight disappears, even though gravity remains. Einstein's theory also changed our understanding of time. In Newton's universe, time flowed uniformly everywhere, unaffected by motion or gravity. General relativity revealed that time passes differently depending on the strength of the gravitational field. A clock closer to a massive object ticks more slowly than a clock farther away. This effect, gravitational time dilation, is small in everyday life, but measurable and essential for accurate technologies. Satellites in Earth orbit carry atomic clocks that run faster than identical clocks on the ground. Global Positioning System receivers must correct for this difference to determine location accurately. Without general relativity, navigation systems would quickly become unreliable. Time itself is intertwined with gravity in a way that Newton's framework could never describe. Einstein's theory also predicted that gravity would influence the path of light. Although light has no mass, it follows the geometry of spacetime just as massive objects do. When light passes near a massive object, its path curves. This prediction was confirmed during a solar eclipse in the early 20th century, when astronomers measured the apparent shift of stars near the sun's edge. The amount of bending matched Einstein's prediction and exceeded what Newtonian physics allowed. This observation was one of the first major confirmations of general relativity and brought international attention to the theory. Subsequent measurements using radio waves and other forms of electromagnetic radiation confirmed the effect with increasing precision. Another powerful test came from studying the motion of Mercury. Newtonian physics could not account for the small extra precession in Mercury's orbit, but general relativity explained it naturally. The curvature of spacetime near the Sun alters Mercury's path just enough to produce the observed precession. This success demonstrated that the geometric understanding of gravity was not only elegant but necessary. No adjustment to Newton's laws could account for the discrepancy. Only a new framework could. Einstein's ideas also transformed the way scientists saw the universe on larger scales. The bending of spacetime predicts that massive objects can act as gravitational lenses, magnifying and distorting the light from distant galaxies. This effect has been observed countless times through modern telescopes. It allows astronomers to study galaxies that would otherwise be too faint to detect and to map the distribution of mass in galaxy clusters. Again, these observations confirm that gravity manifests through geometry. The transition from Newton to Einstein does not diminish the importance of Newton's theory. In most everyday situations, general relativity reduces to Newtonian gravity with remarkable accuracy. The two frameworks are consistent, with general relativity offering a deeper foundation that becomes important when gravity is strong, velocities are high, or precision is crucial. But the shift in perspective is profound. Weight becomes a reaction. Gravity becomes geometry. And the universe becomes a landscape shaped not by forces pulling across space, but by the curvature of space-time itself. In the next part, we explore the meaning of free fall within this geometric framework and examine how general relativity explains the sensation of weightlessness in orbit, the difference between inertial and gravitational mass, and the deep connection between motion and geometry that defines gravity at its core. Einstein's work led naturally to a question that sounds simple, but reveals a profound truth. If gravity is geometry, and free fall is the natural motion through that geometry, what does it mean to be weightless? The answer lies not in the absence of gravity, but in the absence of resistance. A freely falling object feels no force because nothing interrupts its path. It follows a geodesic, the closest thing to a straight line that exists in curved space-time. Inside a falling elevator or orbiting spacecraft, objects drift calmly because everything in that environment shares the same motion. The floor no longer pushes upward. The body no longer senses pressure in the feet or tension in the muscles. The familiar feeling of weight disappears, and the mind must adjust to a new kind of motion that is both liberating and disorienting. This understanding dissolves the common misconception that astronauts float because they are far from Earth's gravity. In truth, they orbit within a strong gravitational field. Earth's pull at the altitude of the International Space Station is only slightly weaker than it is on the ground. What creates the sensation of weightlessness is the continuous free fall around the planet. The spacecraft and everything inside it fall together at the same rate, tracing a curved path that keeps them perpetually missing Earth's surface. In this state, there is no support force acting on the astronauts. Their bodies encounter no upward push, and so they feel weightless. Gravity is present, but weight is not. This distinction captures the essence of Einstein's insight that weight is not a fundamental feature of matter. It is a reaction to being prevented from moving naturally through space-time. To understand this at a deeper level, imagine two observers in different situations. One stands on Earth's surface, feeling the firm pressure of the ground beneath their feet. The other floats freely in orbit, experiencing no push and no strain. In Einstein's framework, the observer on Earth is actually accelerating. The ground forces them away from the geodesic that gravity dictates, producing the sensation of weight. The orbiting observer, by contrast, is not accelerating. They follow a geodesic, experiencing no resistance and therefore no weight. This reversal of intuition is one of the most powerful shifts that general relativity introduces. It reveals that what we traditionally considered motionless under gravity is in fact a state of continuous resistance, while free fall is the true state of unforced motion. This idea becomes clearer when considering the difference between inertial and gravitational mass. Inertial mass measures how strongly an object resists acceleration when a force acts upon it. Gravitational mass measures how strongly an object responds to gravity. The remarkable equality of these two masses, confirmed through precise experiments, is not an accident. It is a reflection of spacetime's role in guiding motion. Because gravity is not a force, it does not distinguish between objects. All objects in the same region of spacetime follow the same geodesic if no other forces act. The equality of inertial and gravitational mass becomes a natural consequence of geometry rather than a coincidence that requires explanation. General relativity reshaped not only how scientists understood motion, but also how they understood energy. In Newtonian physics, gravitational potential energy exists because gravity acts as a force at a distance. In Einstein's framework, potential energy emerges from the geometry of spacetime. An object held above the ground has more potential energy because the geometry shapes different possible paths for the object. When the object is released, it follows the geodesic that nature selects based on energy and curvature. The conversion of potential energy into motion is not driven by a force pulling downward. It is driven by the shape of space-time, guiding the object along a natural path. This geometric view also provides a new understanding of gravitational redshift, a phenomenon in which light climbing out of a gravitational field loses energy and shifts to longer wavelengths. In Einstein's theory, this effect arises because time flows differently in different gravitational environments. A light wave emitted near a massive object must adjust to the slower passage of time in that region, compared to the region where it is received. This shift has been measured experimentally on Earth using precise atomic clocks positioned at different heights. It is also observed in the spectra of stars and in signals received from spacecraft. These confirmations show that the curvature of spacetime affects not only the motion of objects, but also the behavior of light and the flow of time itself. Another powerful confirmation of general relativity comes from studying light passing near massive bodies. The bending of light, first measured during a solar eclipse, has become a cornerstone of modern astronomy. Massive galaxies and clusters of galaxies act as gravitational lenses, magnifying and distorting the light from objects behind them. These lensing effects reveal the distribution of mass in the universe, including mass that cannot be seen directly. They also allow astronomers to study galaxies far more distant than would otherwise be possible. Every observation confirms the predictions of general relativity with remarkable accuracy. Yet perhaps the most profound aspect of Einstein's insight is what it reveals about weight. Weight is not a measure of how strongly gravity acts on an object. Gravity acts on objects regardless of whether they feel anything at all. Weight is a measure of the support force that resists natural motion. It is a response, not a cause. This means that the sensation we use to anchor ourselves in the world is not a direct experience of gravity, but a biological interpretation of mechanical resistance. When you stand on the ground, you feel the upward push of the surface, not the downward pull of gravity. When you fall freely, you feel nothing, even as your motion is shaped entirely by the geometry around you. In this framework, weight becomes a perspective-dependent quantity. Two observers in different states of motion can disagree about whether an object has weight. A person standing inside a rocket, accelerating upward, feels heavy. A person drifting in free fall feels weightless. Both experiences are real, yet neither reveals the full nature of gravity. Einstein showed that to understand weight, one must understand motion, and to understand motion, one must understand geometry. With this knowledge, we now stand at the threshold of a deeper exploration. The next chapter will reveal why weight is not only a reaction, but also a physical response to resisting acceleration through curved space-time. It will show how the experience of weight shapes our everyday world, and why the absence of weight reveals the true structure of gravity. The moment we shift from Einstein's insight to the physical experience of weight, the world begins to look different. The familiar sensation we feel every day, the downward pressure in our feet and the heaviness in our muscles, is not a signal of gravity pulling on us. It is the story our bodies tell as they push back against the world that prevents us from following the path that space-time sets for us. Standing still feels natural, yet physics reveals that it is anything but. To remain motionless on Earth's surface is to resist the natural geodesic that space-time offers. This act of resistance is continuous and invisible, expressed through a force we interpret as weight. Imagine standing on a quiet mountainside. The rocks beneath your feet feel solid and unmoving. The breeze brushes your face lightly, and the world seems calm. But under the surface of this calm lies a constant physical exchange. Every moment, the ground pushes upward with a force that matches the tendency of your body to follow the curvature of space-time toward Earth's center. Gravity is not pressing you downward. Instead, it shapes the geometry you would naturally follow. The sensation of weight appears only because the solid ground prevents that motion. You are not being pulled down. You are being pushed up. This perspective becomes clearer when you consider what happens the instant that support vanishes. If the mountain beneath your feet suddenly disappeared, you would not feel a sudden increase in force. You would feel nothing at all. Your stomach would rise, your limbs would loosen, and your body would shift into a state of free fall. In that moment, gravity would still shape your path, but no internal sensation would tell you so. You would drift in perfect silence within your falling frame, unaware of the gravitational field through which you moved. The weight you once felt would vanish, because the resistance that created it would be gone. This reveals that weight has nothing to do with gravity acting on your mass. It arises only when something stops you from moving naturally. This principle is demonstrated beautifully in the experience of astronauts orbiting Earth. The gravitational field at their altitude is strong, only slightly weaker than it is on the surface. Their bodies experience nearly the same curvature of space-time that people on Earth do. Yet astronauts float effortlessly, drifting from wall to wall with no sense of heaviness. The difference lies not in the gravitational environment, but in the presence or absence of support. The spacecraft and the astronauts inside it fall together, following a shared geodesic. No surface pushes upward on their feet. No muscles resist unwanted tension. In free fall, the body experiences no weight because there is no normal force to interpret. The normal force, the upward push from a supporting surface, is the true physical definition of weight. A bathroom scale measures this force, not the pull of gravity. When you step onto the scale, the springs inside compress as the surface pushes against your feet. The scale reports that upward force to you as a number. If you were falling freely and stepped on the same scale, it would register nothing, even though your mass and the gravitational field around you remain unchanged. This simple instrument reveals the essence of weight with perfect clarity. It is the response of matter to being held out of free fall. This understanding of weight also explains why certain everyday experiences feel strange, even though nothing unusual has happened to gravity itself. When an elevator begins to ascend, you feel briefly heavier. The floor accelerates upward, pushing on your feet with more force than it provides during rest. Your body interprets this increased support force as greater weight. When the elevator slows or begins to descend, the push weakens. You feel lighter, almost floating for a moment. The gravitational field has not changed. The geometry of space-time has not changed. What has changed is the acceleration of the surface beneath you. Your experience of weight is tied to this interaction, not to gravity's pull. The same principle explains why roller coasters create moments of soaring lightness and crushing heaviness. As the car crests a hill and begins to drop, the seat's upward push diminishes. Your body approaches a state closer to free fall, and your sense of weight fades. When the track curves sharply upward again, the seat must push harder to change your motion. You feel heavier, not because gravity grows stronger, but because the support force increases. The track manipulates your sense of weight by shaping the forces required to restrain you from your natural path. Airplanes also create subtle shifts in perceived weight. During turbulence, rapid changes in the aircraft's vertical acceleration can cause momentary fluctuations in the support force acting on your body. A sudden drop produces a brief sensation of near weightlessness as the seat pushes upward with less intensity. A sudden rise produces a quick pulse of heaviness as the seat pushes harder. These momentary sensations reveal the reactive nature of weight. They illustrate that what we feel depends entirely on how much a surface resists our motion, not on the gravitational field alone. All of these experiences share a single unifying truth. Weight is not a property of an object. It is a relationship between the object and the surface that supports it. The moment that surface stops resisting, the weight disappears even though gravity remains. This distinction between gravitational influence and support force is central to understanding how general relativity transforms the meaning of weight. It allows us to see that weightlessness is not an exotic condition limited to space, but a natural state whenever support is removed. Yet this realization raises a deeper question. If weight is a response to resisting natural motion, and natural motion is defined by the geometry of space-time, then weight becomes inseparable from perspective. Two observers in different states of motion encounter different support forces and therefore disagree about what weight means. A person in free fall feels nothing. A person standing still feels everything. Neither perspective is more real than the other. Each reflects the relationship between the body and the path that space-time prescribes. In the next part, we will explore how proper acceleration distinguishes genuine physical forces from the geometric guidance of space-time. We will see why standing still requires continuous acceleration and why weight is the unmistakable sign of resisting the natural paths carved into the universe. To understand why weight arises only when motion is resisted, we must look more closely at the idea of acceleration itself. In everyday language, acceleration means speeding up or slowing down. In physics, however, acceleration has a deeper meaning. It describes how an object's velocity changes in magnitude or direction. Even moving at a constant speed along a curved path counts as acceleration because the direction of motion changes. Einstein recognized that this kind of acceleration, which alters the natural path of an object, is fundamentally different from the acceleration caused by free fall. Free fall does not produce the sensation of acceleration because no force acts on the falling object. The object is not being pushed or pulled. It simply follows the geodesic defined by space-time curvature. This leads to the concept of proper acceleration. the kind of acceleration you can feel. When you stand on the ground, the surface prevents you from following your natural geodesic. The ground must accelerate upward relative to your natural path, and your body senses that as weight. When you sit in a car that suddenly speeds up, your back presses against the seat because the seat must push you forward, preventing you from remaining in your original state of motion. These sensations reveal proper acceleration. They reveal the presence of a force acting on your body. By contrast, when you fall freely, you feel nothing because your body follows the path space-time prescribes. You experience no proper acceleration, even though your speed and direction may change relative to the ground. This distinction explains why astronauts floating in orbit feel weightless even though they move at tremendous speed and remain within a significant gravitational field. They feel weightless because they experience no proper acceleration. Every part of their motion aligns with the geometry of space-time. Nothing pushes on them or alters their path. Meanwhile, a person standing still on Earth feels heavy because every moment the ground exerts a proper acceleration upward, pushing them away from the geodesic they would otherwise follow. This continuous upward push is subtle and invisible, yet it shapes every step we take and every action we perform while standing still. It is the root of the physical sensation we call weight. Understanding this helps clarify why scales measure weight by reporting the support force rather than gravitational attraction. A scale does not measure how strongly gravity acts on your mass. It measures how strongly the scale must push upward to prevent you from falling. When you lean forward or shift your balance, the reading changes because the distribution of support force changes. If you lie flat on your back, the scale's reading changes again because the support force spreads differently across your body. The gravitational field stays the same, but the reaction to resisting motion changes. This is why weight is inherently tied to contact and resistance rather than gravitational pull. These ideas also explain why weight disappears instantly when proper acceleration vanishes. Consider the moment a roller coaster car crests a hill and begins to drop. For a brief instant, the car follows a path close to its natural geodesic, and the seat no longer needs to push upward strongly. Your sense of weight fades because the proper acceleration drops. In the extreme case of free fall, the seat provides no support at all, and the sensation of weight disappears completely. Even though gravity guides your motion, you feel no heaviness because nothing interrupts your path. What you feel is not gravity, but resistance. Everyday objects obey the same principles even when we do not notice them. A book resting on a table presses downward with its weight, and the table pushes upward with an equal force. This upward force exists not because gravity demands it, but because the table resists compression. If the table were to collapse, the support force would vanish, and the book would fall freely, losing its weight immediately. Gravity has not changed. What changes is the presence of the surface that resists. This relationship highlights how deeply weight depends on the physics of support rather than the physics of attraction. This concept becomes even more striking when considering that standing still on Earth actually requires continuous acceleration. Although we do not move upward, the ground must constantly push us away from the geodesic that space-time dictates. This push registers in our bodies as weight. If the push stops, even for a fraction of a second, weight vanishes. This reveals an unexpected truth. Standing still is not a state of rest. It is an active, continuous state of resisting the geometry of space-time. Free fall, by contrast, is the closest thing to rest because it requires no force to maintain. In that sense, falling freely is the true inertial state under gravity. The implications of this idea extend to everything from amusement park rides to scientific experiments. When scientists drop objects in tall vacuum chambers to study free fall, the objects become weightless, not because gravity is removed, but because support is withdrawn. In these facilities, researchers study combustion, fluid behavior, and biological responses under weightlessness. The results match those observed in orbit because weightlessness emerges from the absence of resisting force, not from distance from Earth. This demonstrates that the concept of weight remains entirely consistent from everyday environments to controlled scientific settings. Airplane pilots experience similar effects when performing parabolic flights. During the upward and downward arcs of these maneuvers, forces vary in a way that simulates increased weight, reduced weight, and complete weightlessness. At the peak of the parabola, the aircraft and everyone inside follow a free-fall trajectory. They feel weightless for a short time, even though the airplane remains well within Earth's gravitational field. The pilots have not changed gravity, they have changed motion. These flights reveal that weight is a product of acceleration and resistance, not a direct signal of gravitational strength. All of these examples converge on the same conclusion. Weight is a reaction. It is the physical response of matter to being prevented from following the natural motion that gravity prescribes. It emerges from proper acceleration and disappears in its absence. In Newtonian terms, weight seemed like a straightforward force caused by gravitational pull. But in Einstein's world, weight becomes a record of the struggle between natural motion and resistance. It is an effect, not a cause. It is a consequence of contact, not a property of mass. In the next part, we will bring these ideas together by exploring how proper acceleration defines the boundary between standing still and falling freely. We will see why weight varies across environments, how motion shapes experience, and why resistance reveals more about our perspective than about gravity itself. The idea that weight is a reaction rather than an inherent property becomes even clearer when we look closely at how different environments reshape the support forces our bodies encounter. On Earth's surface, the support force remains steady because the ground is rigid and unyielding. But as soon as that support becomes flexible or variable, the sensation of weight begins to shift. When you stand on a trampoline, your feet sink slightly, and the supporting fabric stretches in response to your mass. The trampoline pushes back, but not with the same consistency as solid ground. As it stretches and rebounds, your sense of weight changes moment by moment. These changes do not reflect variations in gravity, but variations in resistance. The altered sensation comes entirely from the physics of the surface beneath you. This becomes even more pronounced when you jump from the trampoline and experience a momentary pause in resistance. As you rise through the air, your feet no longer press downward against anything. Your body enters a brief interval of free fall, and during that time, you feel weightless. Gravity continues to guide your motion, yet your body registers no heaviness at all. The instant your feet contact the trampoline again, the sensation returns abruptly as the fabric stretches and pushes back. This simple sequence of events captures the essence of weight as a surface-based reaction. It appears when you resist the geodesic and disappears the moment you stop resisting. Every kind of support behaves this way, even those designed to feel firm. A mattress shifts beneath you, distributing weight across different points of contact. A cushioned chair adapts to your shape, altering how much force it applies. These variations demonstrate that weight is not the same thing as gravitational pull. It is the mechanical partnership between your body and the surfaces that must continually fight against the geometry of space-time. If the surface pushes more, you feel heavier. If it pushes less, you feel lighter. If it does not push at all, you feel nothing. Gravity remains constant throughout. The support determines sensation. This truth appears in more surprising ways as well. When a car turns sharply, your body leans to one side because the seat and the door push against you to alter your direction. Even though gravity has nothing to do with this lateral change in motion, the force you feel resembles weight. This is because weight is not limited to vertical forces. It is any force that resists your natural motion. During a turn, the direction of your motion changes, and the surfaces that restrain you create a sideways support force. Your body interprets that resistance as heaviness, even though the gravitational field around you has not changed at all. This illustrates that weight, in a physical sense, arises from any deviation from a geodesic, no matter the direction. Airplane turbulence provides another revealing example. When the aircraft suddenly drops, your seat briefly stops pushing upward with the same intensity. In that instant, your sense of weight fades. When the aircraft rises sharply again, the seat must push harder to redirect your motion, and you feel heavier. None of these sensations come from changes in gravitational pull. They come entirely from changes in support. Turbulence is a dance of forces between your body and the seat that holds you, each fluctuation shifting your perceived weight, even as the gravitational field remains stable. All these examples reinforce the same idea. The body never senses gravity directly. It senses support. It senses interruption. It senses the forces required to keep it from following the natural motion dictated by space-time. This is why astronauts describe weightlessness not as a lack of gravity, but as a lack of pressure, a lack of tension, a lack of being held in place. They say it feels as though the body has forgotten how to be heavy. Muscles relax, joints loosen, the sense of up and down dissolves. These sensations reveal the absence of proper acceleration, not the absence of gravitational influence. In Einstein's world, standing on the ground becomes an act of continuous acceleration. The ground pushes upward, preventing your body from following its geodesic. That persistent push is what you feel as weight. Free fall becomes the opposite. It is the state in which no surface interferes with your motion. You accelerate toward Earth's center, but you feel nothing because no support acts on you. This reveals an extraordinary truth. Under gravity, standing still is physically more strenuous than falling freely. Standing still requires a constant resistance force. Falling requires none. This insight reshapes our understanding of everyday life. Each time you walk, sit, stand, or climb stairs, your body interacts with surfaces that continuously oppose the motion space-time prescribes. The familiar sensations we associate with gravity are in fact sensations of interference. The environment refuses to let us fall, and our bodies interpret that refusal as weight. This means that weight does not reflect how gravity acts on us. It reflects how we act against gravity's geometry. It is a negotiation between the body and the world, not a property of mass. Recognizing this distinction allows us to understand why weight varies across different planets and moons. On a massive planet, the surface must push upward with greater force to counter the steep curvature of space-time near the planet. On a small moon, the required support force is weaker. The gravitational field strength determines the geodesic, and the surface's response determines the sensation. Two people with identical mass may weigh differently on different worlds because each surface provides a different upward push. The difference lies not in them, but in the environment's resistance to their motion. This leads naturally to the notion that weight is tied not only to location, but also to motion. A person on a rotating space station may feel a force pressing them outward, which becomes their artificial weight. A person accelerating in a spacecraft feels a force pressing them into their seat, which mimics weight. These sensations arise from the need to resist certain motions, not from the gravitational pull of a planet. The universality of this idea shows how deeply weight depends on perspective and support, and how little it depends on gravity itself. We now stand ready to explore what happens when gravity becomes extreme. In the next chapter, we will examine environments where space-time curvature grows so intense that everyday intuition breaks apart. Near neutron stars and black holes, the rules remain the same, but the consequences become extraordinary. Weight stretches, twists, and even disappears in ways that challenge imagination, while remaining grounded entirely in physics. When we leave the gentle gravitational fields of Earth and travel, in imagination, toward the most massive and compact objects in the universe, the familiar rules of weight and resistance begin to transform. Nothing breaks the laws of physics, yet everything feels different. The predictable sensations we experience on Earth, the steady pressure of the ground beneath our feet, the stable sense of direction given by the downward pull, all begin to fade as space-time curves more sharply. Gravity does not change its nature, but its consequences grow profound. To understand weight in such places, we must follow the same principles we already know, but we must extend them into realms where curvature dominates every motion and every sensation. Consider first a world not too different from our own, but dramatically denser. A neutron star compresses more mass than the Sun into a sphere only about as wide as a city. The curvature of space-time near such an object is immense. If you were to stand on its surface, the required support force would become unimaginably large because the natural geodesic would plunge steeply inward. Your body would want to follow that path so strongly that no known structure could provide the upward push needed to resist it. In this environment, weight becomes not merely heavy, but catastrophic. Matter itself strains and stretches under the immense support force. Yet even here, the rules are unchanged. Weight is still the reaction to resistance. The difference lies in how much resistance is required to counter the curvature. This brings us to tidal forces, another aspect of gravity that grows increasingly pronounced in strong fields. Tidal forces arise not from the strength of gravity alone, but from its variation across space. On Earth, the difference in gravitational pull between your head and your feet is so small that you never notice it. Near a neutron star or a black hole, this difference becomes significant. Your feet, closer to the mass, would follow a geodesic that curves more sharply than the one your head would follow. If no support holds you together, your body stretches along the direction of the gravitational gradient and compresses sideways. This phenomenon, often called spaghettification, is not a fanciful idea, but a precise consequence of space-time geometry. Tidal forces reveal something crucial about weight in extreme environments. Weight does not vanish simply because gravity is strong. Instead, the forces required to maintain structural integrity increase in astonishing ways. If you attempted to hover near a neutron star using any conceivable device, the support force needed to resist free fall would exceed any material strength. You would feel unbearable weight, not as a simple heaviness, but as a tearing gradient across your body. The scale readings that feel ordinary on Earth would escalate into impossibly large values. And yet, if you were to fall freely near the neutron star, the sensation of weight would vanish instantly. Gravity's influence would be stronger than anything you have ever experienced, but your body would feel nothing because no surface would exist to resist your path. This stark contrast illustrates a profound truth. Even in the most extreme gravitational fields known to science, weightlessness arises whenever free fall is allowed. Gravity may stretch and twist space-time, but the sensation of weight always depends on support and resistance. This is why astronauts on deep space missions would remain weightless, even if they ventured into regions where gravity curves space-time in dramatic ways. The environment might distort time, shift trajectories, and bend light. But if the astronauts remained in free fall, the absence of support force would prevent any feeling of heaviness. The body would sense no pressure, no strain, no clue to the violent curvature it was passing through. Nowhere does this idea become more striking than near a black hole. A black hole is not a place where gravity pulls infinitely. It is a region where space-time bends so steeply that all possible paths lead inward. The event horizon marks the boundary beyond which no trajectory can escape. It is not a physical surface, but a geometric threshold. As you approach it, your experience of weight does not suddenly spike or vanish. Instead, it depends entirely on how you move. If you fall freely past the horizon, you feel no additional force, no sudden shift, no tearing sensation at the boundary. Weightlessness persists as your body continues following its natural geodesic. The extreme nature of the space-time around you does not change the rule. Proper acceleration remains the key to weight. If, however, you attempt to hover near the horizon rather than fall freely, the support force required to resist the natural motion becomes enormous. A spacecraft trying to stay in place would need engines that grow exponentially more powerful as it nears the horizon. The closer it gets, the harder it becomes to provide the proper acceleration needed to remain stationary. If you stood on a hypothetical platform hovering near a black hole, the weight you felt would increase without bound as the platform approached the horizon. The support force required would become infinite at the boundary, making it impossible for anything to resist the geodesic at that location. This is why weight near a black hole becomes undefined at the horizon. No surface can exist there that resists freely falling motion. These ideas might seem strange, even counterintuitive, yet they arise directly from Einstein's equations and have been confirmed through observations. Scientists have detected gravitational waves produced when massive objects like black holes merge. These waves ripple outward through space-time, carrying energy and revealing the dynamic curvature that general relativity predicts. The detection of these waves offers some of the most direct evidence we have for the existence of extreme gravitational environments. They show that space-time bends, stretches, and compresses in ways that match Einstein's theory precisely. The images captured by the Event Horizon Telescope also confirm that light circles black holes along curved paths that reveal the geometry of space-time. We observe shadows and rings of glowing matter shaped by the immense curvature, not by invisible forces pulling matter inward. Even within our own solar system, variations in gravitational strength illustrate the diversity of weight that humans would experience across different worlds. On the Moon, the support force required to resist motion is only a fraction of what it is on Earth. On Mars, it lies somewhere in between. On Jupiter, a solid surface that could support a human does not exist, but if it did, the weight felt would be far greater than anything experienced on Earth. This variation arises because the curvature of space-time differs from one location to another. The strength of the required support force changes accordingly. Weight becomes a measure of the environment, not the object. All of this leads to a single powerful realization. Gravity behaves consistently everywhere in the universe, from gentle fields to the most extreme environments imaginable. But the way we experience weight changes depending entirely on how we move and what resists our motion. In the deepest gravitational wells, free fall remains weightless, and resistance becomes impossible. In weaker fields, surfaces can provide resistance, creating the familiar sense of weight. These variations arise not because gravity changes its rules, but because observers live different stories depending on their motion. In the next part, we will follow these consequences even further, examining how the observer's point of view determines the meaning of weight and why gravity remains consistent even as experience diverges dramatically across the universe. As we journey deeper into the realm of intense gravitational fields, we discover that the meaning of weight depends not only on resistance, but also on perspective. Two observers can occupy the same region of space-time and yet describe completely different experiences. One may feel overwhelming weight, while the other feels nothing at all. This difference does not arise from conflicting realities, but from the simple fact that weight is not an inherent property of matter. It is a record of how each observer interacts with the curvature around them. Nowhere is this more apparent than near massive cosmic objects that distort space-time far more dramatically than anything on Earth. Imagine two individuals approaching a neutron star. One remains inside a spacecraft that attempts to hover above the surface. Its engines fire continuously, pushing the craft upward and resisting the steep inward curve of space-time. The pilot inside feels the support force generated by the seat beneath them. That force grows stronger as the craft moves closer to the star. Even when the engine output remains steady, the pilot feels their weight increase because the geodesic they must resist becomes steeper. The pilot might describe the sensation as crushing heaviness. The instrument panels might display rising values that reflect the growing proper acceleration. Yet if another individual simply exits the craft and falls freely toward the neutron star, that person feels none of this heaviness. The gravitational field is the same for both observers, but the experience diverges entirely. The falling individual follows the geodesic shaped by space-time and therefore experiences no weight. The hovering pilot constantly fights against that path and therefore experiences intense weight. This contrast highlights a crucial truth. Weight is not a universal quantity. It varies from observer to observer, depending on their motion and their interaction with the environment. In a weak gravitational field, like that of Earth, these differences are subtle. In an extreme field, they become overwhelming. Yet the underlying rules do not change. The physics of weight in everyday life and the physics of weight near a neutron star are governed by the same principles. The only difference is the dramatic curvature that amplifies the consequences. The same difference in perspectives occurs near a black hole. A person who falls freely across the event horizon experiences no change in weight as they cross it. The threshold is not a wall. It offers no resistance. From their point of view, nothing special happens at the horizon. They simply continue along their geodesic. But a person trying to hover just above the horizon faces a completely different reality. The support force required to remain stationary grows rapidly as the horizon nears, and no physical structure can provide the necessary resistance at the boundary. Weight grows without limit. The hovering observer would describe an environment of impossible pressure and crushing force. And yet, just a short distance away, the falling observer feels nothing at all. Both describe the same space-time, but they tell different stories because weight depends on resistance, not the gravitational field itself. These contrasts reveal how important it is to distinguish between conditions in space-time and experiences within space-time. Physics describes the underlying structure, while observers experience only the effects that surfaces, forces, and motion impose on them. When a person stands on Earth, they interpret the support force as absolute weight. When the same person falls freely, they interpret the absence of support as weightlessness. Neither interpretation reveals the underlying geometry directly because the body senses only contact forces. It cannot feel gravity itself. This separation between environment and experience becomes essential when interpreting extreme astrophysical phenomena. Consider the stretching forces near a black hole, the tidal forces that pull objects apart along one direction and compress them along another. These forces express variations in the curvature of space-time. If you fall freely toward the black hole, you would feel these distortions only gradually, depending on the size of the black hole. A supermassive black hole with millions of times the mass of the Sun produces gentle tidal forces near its horizon. You could cross the boundary without feeling any disruptive effects. Only deeper inside would the gradient become strong enough to stretch your body noticeably. Near a smaller black hole, however, the tidal gradient becomes severe even before you reach the horizon. The same principle applies to weight. The gravitational field near both objects can be equally overwhelming, but the experience of weight depends on how you interact with the geometry. Free fall hides gravity's presence. Support exposes it. Scientific evidence for these extreme conditions comes not from imagination, but from precise measurements. Gravitational waves, detected by observatories on Earth, offer a direct glimpse into the motion of massive objects spiraling toward one another. When two black holes merge, the violent reshaping of space-time sends ripples outward. These waves carry information about mass, motion, and curvature. They confirm that space-time behaves exactly as Einstein predicted, even in the strongest known gravitational fields. Observations of neutron stars, pulsars, and accreting matter near black holes also reveal the extraordinary consequences of enormous curvature. The light from these objects shifts in frequency as it climbs out of deep gravitational wells, confirming gravitational redshift. Matter near black holes follows twisted orbits that reveal the shape of space-time. Every observation anchors the idea that gravity expresses itself through geometry rather than force. Yet in every one of these environments, the experience of weight still depends entirely on resistance. If no surface resists the natural path, weight vanishes. If a surface attempts to hold its position, weight grows to match the required acceleration. Near a neutron star, that support force becomes immense. Near a black hole, it becomes impossible. The geometry shapes motion, and weight reflects the opposition to that motion. This universality is one of the most remarkable features of general relativity. The same ideas that explain why you feel heavier when an elevator accelerates explain why weight becomes infinite near a horizon. To appreciate the magnitude of these effects, imagine attempting to land on a neutron star. The curvature of space-time is so steep that the geodesic plunges inward with immense force. Any vehicle attempting to remain stationary would require constant acceleration. The support force needed to counter that path would be far beyond the capacity of any material. A person standing on the surface would feel crushing weight not because the neutron star exerts an intense downward pull in the Newtonian sense, but because the surface must resist an overwhelming geodesic. If that surface were removed, free fall would eliminate all sensation, even as the motion became catastrophic. The difference lies entirely in support. This is the heart of extreme gravity. The structure of space-time dictates how objects move. Weight becomes the body's memory of resisting that motion. And as curvature intensifies, so does weight, until resistance becomes impossible. Observers do not disagree because physics contradicts itself. They disagree because weight is perspective. It is the personal report of how much force must be applied to remain off the geodesic. In the next part, we will explore how these extreme environments reveal the deeper truth that perspective is physical, not philosophical. Observers in different states of motion inhabit different experiences of weight, even when describing the same gravitational field. This prepares us for understanding how frames of reference shape the meaning of gravity itself. As we reflect on these extreme gravitational environments, a deeper pattern begins to emerge. The laws of physics remain perfectly consistent from the gentlest fields to the most violent. Yet the experiences of observers diverge more dramatically with each increase in curvature. The same space-time can feel crushing to one observer and completely weightless to another. The difference lies entirely in motion and resistance. This realization forces us to reconsider what it means to describe a physical environment. Two people can witness the same astronomical phenomenon, trace the same paths in theory, and still report experiences that seem to contradict one another. And yet there is no contradiction, there is only perspective. Imagine three observers positioned near a massive black hole. One hovers at a fixed altitude in a spacecraft, fighting continuously against the inward bending geodesic. The engines roar, the hull vibrates, and the pilot inside feels a heavy force pressing them into their seat. Instruments strain as the proper acceleration grows. To this observer, the region feels violently oppressive, a place where weight grows without mercy and time seems distorted. A second observer floats freely past the same location, experiencing nothing but calm motion. They drift silently, feeling no pressure on their body as the curvature guides their path inward. They see the spacecraft straining above them and know that both of them occupy the same region of space-time, yet their sensations differ completely. A third observer in a distant orbit watches both and perceives entirely different motions shaped by their own frame of reference. Each observer describes the same physical geometry, but their experiences diverge because weight arises not from gravity, but from support. This divergence becomes even more striking when we consider how time itself behaves in strong gravitational fields. Clocks closer to massive objects run more slowly than clocks farther away. Time dilation is not a distortion of perception. It is a real physical effect confirmed through countless experiments, from atomic clocks flown on aircraft to observations of stars orbiting black holes. Yet the observer who falls freely into a strong field does not feel time slowing. Their own clock ticks normally. Their own heart beats steadily. Their own thoughts unfold in familiar rhythm. It is only when two observers compare their measurements that the difference becomes evident. Time, like weight, becomes a quantity influenced by perspective. It does not contradict reality. It enriches it. This idea extends to energy as well. To stand motionless near a massive object requires continuous energy expenditure to resist falling. A spacecraft trying to hover near a black hole consumes immense amounts of fuel to maintain its position. The falling observer expends no energy at all. Both describe the same gravitational field, yet one must burn fuel to maintain a condition that feels stationary, while the other drifts effortlessly. This is not a contradiction, but a reminder that motion under gravity has meaning only relative to a chosen frame. When gravity is geometry, there is no universal state of rest. There are only paths through space-time, each perceived differently depending on the observer. All of this reveals why weight is not a fundamental physical quantity. It is not encoded in the curvature of space-time the way the motion of planets or the bending of light is. Instead, weight records a negotiation between an object and a surface, or force, that prevents the object from following its natural path. In extreme gravitational fields, this negotiation becomes intense. The geodesic plunges inwards so steeply that no conceivable support can resist it. Weight grows beyond any limit in these situations, because the resistance required to hold position becomes impossible. Yet in the absence of support, weight vanishes completely, even though the curvature remains. These extremes teach us something profound about the relationship between experience and reality. Our senses evolved in a gentle gravitational environment where weight feels stable and absolute. But beyond Earth, as curvature intensifies and tidal forces grow, weight reveals itself to be entirely conditional. It depends on what we choose to do, where we choose to stand, and how we choose to move. Just as time stretches and contracts depending on perspective, weight appears and disappears depending on resistance. This is why astronauts describe the transition into orbit not as entering a region without gravity, but as entering a region without support. They step into a world where motion aligns with geometry, and the familiar sensation that has anchored human life since its beginning simply ceases to exist. This perspective becomes even more important when we consider the dramatic images captured by modern astronomy. In the glowing rings of matter swirling around black holes, we see the consequences of extreme curvature. Hot gas spirals inward, heating as gravitational energy transforms into motion. The light emitted from these regions is bent and stretched, revealing the shape of space-time itself. Instruments like the Event Horizon Telescope allow us to see this structure indirectly, mapping the shadows and luminous arcs created by matter following curved geodesics. Weight plays no role in these images. What we witness is geometry revealed through light, not force felt by observers. Yet if a physical surface existed in those regions, support would impose unbearable weight upon anything that touched it. These same principles apply at planetary scales. On the Moon, astronauts bounce lightly because the support force needed to resist free fall is small. On Mars, weight lies somewhere between Earth and the Moon. If humans ever stand on a distant exoplanet with stronger gravity, they will feel heavier not because gravity presses on them, but because the surface must push harder to counter the steeper geodesic. Every world shapes its own version of weight, and every observer interprets it differently. The vast diversity of gravitational environments across the universe ensures that weight is one of the most variable sensations a human could ever experience. In the end, the lesson of extreme gravity is that experience tells only part of the story. Gravity acts uniformly on all objects, shaping their motion through space-time. Weight, however, is a dialogue between that motion and the resistance to it. Two observers can feel different things in the same place because they participate in that dialogue in different ways. This realization prepares us for the next chapter, where we examine frames of reference more directly. The idea that perspective changes physical experience is not philosophical speculation. It is the foundation of relativity. Gravity remains consistent. Observers do not. And as we move into the next stage of our journey, we will see how motion itself creates the world each observer inhabits. From the moment Einstein revealed that gravity is geometry rather than force, it became inevitable that motion would take center stage in understanding how the universe behaves. If geometry shapes the paths that objects follow, then the experience of gravity must depend on how each observer moves through that geometry. This idea introduces a subtle but profound shift. We are accustomed to thinking that gravity is the same for everyone, that it acts uniformly regardless of where we stand or how we move. Yet relativity tells a different story. It tells us that two observers can share the same physical environment and still disagree about what they feel and how time flows. Not because physics is inconsistent, but because motion reshapes experience. Imagine once again the astronaut drifting freely in orbit. To this astronaut, the world feels weightless. They float gently, unconstrained by any surface. But to an observer on Earth watching from afar, the astronaut is accelerating continuously, curving around the planet in an endless fall. The observer sees motion guided by gravity, while the astronaut inside the spacecraft feels nothing. Both descriptions are correct. They represent different frames of reference. The astronaut feels no weight because their motion aligns with the geodesic carved by space-time. The observer on Earth sees the curvature of that geodesic as acceleration. These two views, though seemingly contradictory, cannot be reconciled by claiming that one is more real than the other. Instead, relativity teaches us that each frame describes the universe in its own consistent way. This principle extends far beyond orbit. A person standing on Earth feels heavy because the ground pushes upward, preventing free fall. An observer falling freely past them, however, sees the person as accelerating upward, not downward. From the falling observer's frame, the person on the ground does not remain still. They accelerate because the surface pushes them away from the geodesic. Once again, the difference is not philosophical. It is physical. Each observer uses their own motion as the reference by which the world is measured. Gravity appears differently in each case because gravity is not a force transmitted across space. It is the structure through which motion unfolds. To appreciate how deeply this affects understanding, consider what it means to call a frame of reference inertial. In Newtonian physics, an inertial frame is one in which objects move in straight lines at constant speeds unless acted upon by forces. But general relativity reveals that straight lines do not exist in the traditional sense. The straightest possible path is a geodesic, a line that curves through space-time according to the mass and energy present. A freely falling frame is therefore the closest thing to an inertial frame under gravity. It is a frame in which no forces act on the observer. The observer floats, drifts, and measures local physics without interference. Standing on the ground, by contrast, is not inertial. It requires continuous acceleration. The upward push from the surface creates a persistent force that shapes every sensation the observer experiences. This understanding reshapes familiar experiences in unexpected ways. Consider a rotating space station built to simulate gravity. The people inside the station feel a steady outward pressure on their bodies as the structure spins. Their feet press against the outer wall, and they feel as though gravity pulls them toward the floor. But there is no gravitational field inside the station. The sensation arises entirely from motion. The wall provides the support force needed to keep the inhabitants moving in a circular path. To an observer outside the station, watching from a non-rotating frame, the illusion becomes clear. The rotation creates proper acceleration, and the wall supplies the push. To the people inside, however, the sensation is indistinguishable from weight. Locally, their frame behaves as though they stand on the surface of a planet. This equivalence between real gravity and simulated gravity through acceleration lies at the heart of relativity. It explains why an observer in a rocket accelerating upward through empty space feels the same weight as someone standing still on Earth. The rocket's floor pushes against their feet, producing a support force that mirrors the upward push provided by the ground. Inside the rocket, there is no way to determine whether the force comes from gravity or from acceleration. Physics treats both situations in the same way because the observer's frame determines the experience. Only by looking outside the rocket can the difference be revealed. But not all frames are so easily compared. Acceleration can create effects that mimic gravity, but it can also create forces that have no gravitational counterpart. In a rotating frame, for example, objects appear to experience outward forces and sideways forces that do not exist in a stationary frame. These effects arise because rotating frames are not inertial. The changing direction of motion produces apparent forces that act on objects even when no physical interaction occurs. These fictitious forces, though not fundamental, shape the experience of observers inside the rotating frame. They show that motion alone can produce sensations and trajectories that seem real, even though they arise entirely from perspective. Because of this, observers moving differently through space-time can disagree on measurable quantities such as time, energy, and even what it means for two events to occur simultaneously. Special relativity first revealed that simultaneity depends on motion. Two observers relative to each other at different velocities may not agree on whether two distant events happened at the same moment. General relativity extends this idea into gravitational environments. Time flows differently in different frames because curvature changes the rate at which clocks tick. A clock on a satellite runs faster than a clock on Earth. A clock near a black hole runs more slowly than a distant clock. These differences are not illusions. They are measurable and essential for technologies that depend on precision. All of this returns us to weight. If motion and perspective shape the experience of gravity, then weight becomes not only a reaction, but a frame-dependent quantity. Two observers can look at the same object and disagree about whether it has weight, and both can be correct in their own frames. A freely falling observer sees the object as weightless. A stationary observer sees it as heavy. A rotating observer may see it pressed outward toward a wall. The object itself has not changed. The difference arises entirely from the frame through which its motion is interpreted. This reveals the heart of relativity. Physics does not privilege one perspective over another. Instead, it provides tools to translate between them. This idea prepares us for the next part of the journey. If gravity and weight depend on frame of reference, then artificial gravity becomes not a futuristic fantasy, but a practical consequence of controlled motion. By choosing how we move, we choose what we feel. In the next section, we will explore how acceleration creates weight, how engineers envision structures that replicate Earth-like conditions in deep space, and why human experience depends so profoundly on the frame in which it unfolds. The more we explore frames of reference, the more we realize that the universe does not provide a single, universal description of motion. Instead, it offers a network of perspectives, each one anchored to the state of motion of an observer. Some frames glide smoothly along geodesics, sensing no force. Others strain continuously against the shape of space-time, interpreting that struggle as weight. What we call rest and what we call motion depend entirely on the frame we choose. A person seated on Earth may think of themselves as stationary, yet an observer falling freely toward the ground sees that same person accelerating upward. In space, where no surface anchors our intuition, the distinction becomes even more fluid. These differences are not errors, but reflections of relativity's central insight. Motion is relative, and the meaning of weight arises only within a particular frame. To appreciate how dramatically frames influence experience, imagine standing inside a sealed rocket drifting through deep space. With no windows and no external cues, you feel weightless. Every object floats. Your limbs hover at your sides. Then, without warning, the rocket begins to accelerate. You feel the floor push against your feet. A sense of heaviness returns, not because gravity has appeared, but because the rocket's engines change your motion. From your perspective inside the sealed cabin, the force pressing you downward feels exactly like gravity. You cannot distinguish the two experiences because both arise, from resistance to natural motion. If the rocket continues to accelerate steadily, your body adapts, and the environment becomes indistinguishable from standing on Earth. This scenario demonstrates the equivalence principle in its most practical form. It also shows why artificial gravity is not speculative. It arises naturally from motion itself. By accelerating or rotating a habitat, engineers can create conditions that mimic weight. The physics is not imagined. It is the same physics that determines your weight when an elevator begins to rise, or when a car takes a sharp turn. But these familiar examples also reveal something deeper. The support force you feel depends not on gravity, but on how your frame resists acceleration. The direction and magnitude of weight shift depending on how you move, not on where you are in the universe. Frames of reference also affect the flow of time in ways that seem almost mystical until we understand the physics underlying them. A clock inside an accelerating spacecraft ticks differently than one floating freely. A clock on the surface of Earth runs more slowly than a clock in orbit. These effects do not emerge from malfunction or illusion. They reflect the geometry of space-time and the energy required to resist it. Time becomes inseparable from motion. The experience of duration becomes woven into the state of the observer. When astronauts travel in orbit, their biological rhythms unfold slightly differently from those of people on the ground, not because they think differently or sense time differently, but because time itself passes at a different rate in their frame. This idea seems extraordinary until we recognize that it arises from the same principles that determine weight. Whenever we resist the geodesic that space-time dictates, proper acceleration appears. And wherever proper acceleration appears, time behaves differently. Standing on Earth slows your clock compared to the clock of someone far above the surface. The difference is small, but measurable. In high-precision environments, it must be accounted for. This subtle shift reminds us that the experience of weight is not an isolated phenomenon. It is part of a larger tapestry in which motion, time, and geometry converge. The role of frames becomes even clearer when we examine phenomena that appear contradictory at first glance. If you drop a stone from a moving train, someone inside the train sees it fall straight down, while someone standing by the tracks sees it follow a curved path. Both observations are correct because each one uses a different frame of reference. In the same way, an observer in free fall near a black hole may feel no force at all, while an observer hovering nearby experiences crushing weight. Both describe reality accurately from their frame. The stone does not have a single absolute path. The observers do not have a single absolute experience of weight. Physics provides rules for translating between perspectives, but it grants no privileged viewpoint. These examples reveal why gravity itself depends on how we move. In general relativity, gravity does not act as a force. It guides motion through space-time. The support forces we interpret as weight arise only when we resist that motion. Frames of reference therefore determine not only what we feel, but what we measure. An observer in free fall sees no gravitational force acting on them. An observer on the ground sees a continuous upward acceleration imposed by the surface. Both descriptions are valid, and each leads to its own consistent interpretation of physical laws. The difference is not philosophical, but operational. Understanding these distinctions prepares us for environments in which gravity becomes indistinguishable from acceleration. A spacecraft accelerating continuously can simulate Earth-like weight. A rotating space station can create a sense of downward force that feels natural to its inhabitants. Yet someone drifting outside the station sees no gravity at all, only motion. This demonstrates that weight is something we create when we choose a particular frame. It is not a built-in property of objects, but a relationship between objects and motion. These ideas become even more significant when considering how observers measure energy. For one observer, a falling object gains energy as it accelerates. For another observer in free fall, the same object moves calmly at constant energy. In one frame, a stone thrown upward loses energy as it rises. In another, the rising stone follows a natural path through space-time that requires no expenditure. These descriptions do not fight each other. They complement each other by capturing how motion shapes measurement. And yet, despite all these variations, the underlying structure of the universe remains consistent. The curvature of space-time determines geodesics. Observers moving freely follow them. Observers resisting them feel forces. This consistency allows people in different frames to translate between perspectives and arrive at the same predictions. It is this coherence that makes relativity such a powerful framework. It does not erase the differences in experience. It explains them. As we approach the final part of this chapter, it becomes clear that understanding gravity requires understanding frames of reference. To say that weight depends on perspective is not to diminish its reality. It is to clarify its cause. Weight is real for the person who feels it. Weightlessness is real for the person in free fall. These realities differ because the observers inhabit different frames, each shaped by motion and geometry. In the next part, we will bring these ideas together by examining how artificial gravity arises from controlled motion, why observers disagree on energy and time, and how these principles reveal the deeper truth that gravity is inseparable from perspective. This will prepare us for the exploration of artificial gravity in the following chapter, where engineering and human adaptation meet the physics of motion. As we gather these ideas together, a coherent picture begins to form. Gravity, in Einstein's universe, is not something that pulls on objects. It is the shape of space-time guiding all motion. Frames of reference determine how that motion is felt, described, and measured. What we call weight is not a signal of gravity itself, but a response to resisting the geodesic carved by curvature. Once this becomes clear, the universe transforms in our imagination. It shifts from a stage where forces tug invisibly across space to a landscape where geometry defines how everything moves and where observers experience that geometry differently depending on their state of motion. The path that once seemed absolute becomes fluid, dependent on the traveler, and weight, which once seemed intrinsic, becomes a reflection of perspective. This perspective-based nature of weight becomes more apparent when we consider simple, everyday scenarios. Imagine two people standing on opposite sides of Earth. Each feels weight in the direction of the ground beneath their feet. To them, that direction feels absolute. Yet each person points in a different direction in space. Their sense of downward is not universal. It is defined entirely by the surface resisting their free fall. If both stepped into a freely falling elevator shaft, that absolute sense of downward direction would vanish. They would float, unable to identify up or down without looking outside. The shift in perspective does not change the gravitational field. It changes their relationship to resistance. What feels like a universal truth collapses into a relative experience once the surface that provides weight is removed. The same relativity shapes the experience of motion. A person sitting inside a smoothly moving train feels no wind, no push, no hint that the train advances through space. Their frame hides the motion. Only when the train accelerates or decelerates does the passenger feel a push, revealing the presence of proper acceleration. Gravity behaves similarly. A freely falling observer senses no acceleration because their frame aligns perfectly with the geodesic. Only when something resists that alignment does the sensation of weight arise. This symmetry between gravity and motion is why Einstein said there is no experiment inside a small enclosed space that can distinguish between constant acceleration and a uniform gravitational field. The equivalence is perfect at local scales, revealing the unity between weight and motion. These insights shine even more clearly when we examine the behavior of clocks and energy in different frames. An observer standing on Earth experiences time that flows slightly slower than the time experienced by someone orbiting above them. The difference is tiny but measurable with precise atomic clocks. This occurs because the grounded observer resists the natural geodesic, while the orbiting observer follows it. The same support force that produces weight also influences the flow of time. Energy measurements shift as well. A falling stone appears to gain kinetic energy from the perspective of a stationary observer because the stone accelerates relative to their frame. But to the stone itself, no force accelerates it. In its frame, its energy remains unchanged until it encounters resistance. These differences do not arise from confusion or error. They arise because motion shapes measurement, and measurement shapes the story each observer tells. This leads to an important realization. Perspective is not a philosophical abstraction in relativity. It is a physically meaningful part of how gravity operates. When two observers describe different experiences of weight or energy or time, they do not contradict each other. Their accounts reflect the structure of their frames. The differences between their descriptions hold real information. They reveal how space-time curves, how motion unfolds, and how forces arise when natural paths are disrupted. Perspective becomes a lens that exposes the physics rather than conceals it. Understanding this shifts the role of the observer from passive witness to active participant. When we stand on Earth, we participate in gravity by resisting the geodesic. When we fall freely, we step out of that resistance and let geometry guide us. When we accelerate in a rocket, we create a new frame that redefines what weight means inside the cabin. The observer and the environment cannot be separated. Together, they form the context in which weight arises. This partnership between motion and experience becomes the foundation for the creation of artificial gravity. If weight depends on resistance to a geodesic, then creating weight is simply a matter of creating motion that requires resistance. By controlling acceleration or rotation, engineers can mimic the sensations normally provided by planetary surfaces. This turns artificial gravity from an abstract idea into a practical application of relativity. Rotating habitats exploit this very principle. The spinning structure forces inhabitants to move along curved paths. The walls of the cylinder push inward to keep them turning. In their frame, the inward push from the wall becomes the sensation of weight, directed outward toward the hull. To them, it feels as though gravity anchors them, even though no mass beneath their feet generates a gravitational field. The motion itself creates the support force. This example reveals something extraordinary. Artificial gravity does not require manipulating gravitational fields. It requires manipulating frames of reference. The power of frames becomes even clearer in interplanetary travel. A spacecraft accelerating continuously at a steady rate can create a sensation of weight indistinguishable from Earth's surface. Inside the cabin, the floor presses against the astronauts' feet, providing the support they need to maintain posture and movement. To the astronauts, this becomes their new normal. To an outside observer drifting freely nearby, however, the spacecraft streaks past with continuous proper acceleration. Once again, two observers witness different truths because they inhabit different frames. Both truths are valid. Both reveal a facet of how motion and geometry shape experience. All of these insights converge on a single profound conclusion. Weight, motion, time, and energy cannot be separated from the frame through which they are observed. Relativity does not diminish the physical world. It enriches it by showing that the universe is not a static backdrop, but a dynamic environment where experience depends on how we move and what we resist. This understanding now prepares us for the next chapter, where we will explore artificial gravity in detail. There we will see how the physics of motion becomes a tool for shaping human life in space, and how mastery of frames allows us to create environments where weight reappears by design. Gravity depends on perspective, but perspective, in the hands of engineers and explorers, becomes a powerful way to shape our journey into the universe. Artificial gravity begins not with futuristic technology, but with a simple realization born from general relativity. If weight appears only when motion through space-time is resisted, then the experience of gravity can be recreated wherever that resistance is engineered. In the vacuum of space, far from planetary surfaces, humans discovered this truth firsthand. The body does not miss gravity itself. It misses the support force. Muscles long for the steady tension that walking once demanded. Bones anticipate the tiny stresses of each step. The vestibular system waits for the familiar anchor that defines up and down. To restore these sensations, engineers study motion, not mass, knowing that motion alone can bring weight back into the lives of astronauts drifting between worlds. The most promising method for creating artificial gravity is rotation. Picture a vast ring turning silently in space, its inner surface curving beneath the feet of its inhabitants. As the ring spins, each person inside moves along a circular path. Without the structure beneath them, they would drift away, following straight lines into emptiness. But the floor presses upward gently, guiding them along the curve. This upward push becomes their weight. To the mind, it feels no different from standing on Earth. The body responds with relief as muscles engage, blood distributes naturally, and familiar cues of direction return. The illusion is not deceitful. It is physics in motion. Yet rotation introduces complexities that Earth never prepared humans for. The direction of perceived gravity points outward from the axis of rotation, not downward toward a planet. The strength of that gravity depends on how fast the structure turns and how far a person stands from the axis. A large habitat allows a slow, gentle rotation, creating a stable environment. A small habitat requires faster spinning, which can confuse the inner ear and disrupt balance. Engineers must balance structural strength, rotational comfort, biological needs, and mission constraints to create a living environment that feels natural and safe. Linear acceleration offers another path. A spacecraft accelerating steadily in one direction creates a sensation indistinguishable from standing on Earth. The floor presses upward, the body settles into its familiar balance, and weight returns. But continuous acceleration demands energy far beyond current capabilities for long missions. Still, even brief periods of acceleration provide invaluable relief, helping maintain bone and muscle strength during long voyages. Artificial gravity therefore becomes not an imitation of nature, but an extension of relativity. It transforms motion into environment, shaping human experience in places where planets cannot reach. And as humans look toward long missions to Mars and beyond, artificial gravity becomes essential. It is not a luxury, it is a lifeline, binding the needs of biology with the possibilities of exploration. As the chapter closes, a deeper question emerges. If gravity can be created through motion, how does motion shape the human mind and perception itself? That is the path we follow next. The human body carries ancient expectations, written into nerves, muscles, and senses by countless generations under Earth's steady pull. Gravity shaped posture, movement, balance, and intuition long before humans understood its nature. When astronauts leave Earth, they leave that silent foundation behind. In weightlessness, the body enters a world it was never designed to inhabit, and in response, it begins one of the most remarkable transformations in biology. Perception rewrites itself without complaint. The vestibular system, housed deep within the inner ear, is the first to confront the truth of weightlessness. Tiny floating stones that once signaled direction now drift without guidance. They no longer settle downward, because downward no longer exists. Signals that once matched perfectly with visual cues begin to conflict. The eyes say the world is stable, but the vestibular system says the world is adrift. This conflict produces the early waves of space motion sickness, a disorientation not caused by danger, but by the absence of gravity's familiar anchor. The body learns slowly. Vision becomes the primary guide. Astronauts navigate by touch and sight rather than by balance. Arms float effortlessly. Legs no longer carry weight. The body grows longer as the spine decompresses. The sense of self shifts subtly as the boundaries between effort and motion dissolve. Over weeks, these new patterns become normal. Astronauts glide with the grace of swimmers drifting through still water, every movement quiet and deliberate. Yet even as the body adapts, something deeper stirs within perception. Without weight, space loses its hierarchy. Up and down dissolve into directions without meaning. Objects float beside the face rather than resting on surfaces. A sleeping astronaut feels suspended rather than supported. The mind must build a sense of place without gravity's help, relying on memory, structure, and awareness rather than instinct. This transformation touches emotion as well. Some astronauts describe weightlessness as freedom, unlike anything on Earth. Others describe a quiet ache for the grounding force that shaped their entire lives. The absence of weight becomes a presence of its own, a new psychological state. When artificial gravity restores downward force through rotation, the relief is immediate. The floor supports the body once more. Orientation returns. Muscles awaken to familiar tension. The mind settles into patterns shaped over a lifetime. As perception shifts between these states, one truth becomes undeniable. Gravity is not simply a physical condition. It is a cornerstone of human identity. And when it vanishes, humans discover how deeply their sense of reality depends on it. This realization leads naturally to the question at the heart of the next chapter. If weight is so tied to perception, what is the difference between experience and physical reality itself? By now, the gap between what humans feel and what the universe actually does has become impossible to ignore. Experience insists that weight is fundamental, that gravity pulls downward, that motion requires force, that time flows evenly. But general relativity reveals a different world, one where motion is shaped by geometry, where time flows differently from place to place, and where weight arises only when surfaces resist a natural path through space-time. This discrepancy is not a flaw in perception. It is a reminder that the senses evolved for survival, not for decoding the architecture of the universe. A person standing on Earth feels heavy because the ground pushes upward, yet they interpret that push as gravity itself. A person in free fall feels weightless, even though Earth's curvature guides them at every moment. Two observers may occupy the same region of space-time and describe entirely different realities, each correct within their own frame. This relativity of experience extends far beyond weight. Two events that seem simultaneous in one frame may not be in another. A falling object appears to gain energy from the ground observer's perspective, but seems calm and unforced to an observer falling with it. Time itself stretches or compresses, depending on where one stands in a gravitational field. None of these effects register directly in human sensation. They are revealed only through careful measurement and theory. This realization leads to a profound shift. Experience, for all its immediacy, becomes only one way of understanding the world. Physical reality, shaped by geometry and motion, becomes something far larger than sensation can grasp. Understanding gravity requires seeing beyond the body's interpretation and recognizing that weight is not a property, but a relationship. Gravity does not act on objects. Objects move with gravity. Weight appears only when that motion is interrupted. With this shift comes clarity. Perspective is not an illusion, it is a key. Each observer's experience reveals a different aspect of space-time. The falling observer reveals the nature of geodesic motion. The grounded observer reveals the effects of resisting it. Neither is wrong. Both illuminate the structure of gravity. When these insights converge, the illusion of weight dissolves, and the deeper truth emerges. In the final chapter, that truth takes center stage. Gravity is not a force. It is not a pull from above or below. It is the curvature of space-time itself, shaped by mass and energy, guiding everything from planets to photons along paths that appear curved only because the geometry bends beneath them. When humans stand on Earth, they feel weight not because gravity pushes downward, but because the ground pushes upward, preventing them from following the geodesic that space-time prescribes. When they fall freely, they feel nothing, not because gravity disappears, but because they finally move with it. Einstein's field equations capture this truth with mathematical precision. They describe how matter tells space-time how to curve and how curvature tells matter how to move. From these equations arise the orbits of planets, the slowing of time in gravitational wells, the bending of light, the stretching of space itself. Every observation across the last century confirms this picture. And yet, for all its depth, the sensation of weight remains separate from it. Weight is a reaction, an emergent experience created only when motion is resisted. This understanding brings the journey to its conclusion. Gravity is geometry. Weight is perspective. And the universe becomes clearer when we separate the two. The body may insist that weight defines gravity, but physics reveals that it is only the story the body tells when resisting nature's preferred motion. In orbit, weight vanishes, but gravity remains. Near a black hole, time slows even when the body feels nothing. Across the cosmos, gravity shapes the evolution of galaxies, while sensation plays no role at all. And yet, this distinction does not diminish the meaning of experience. It deepens it. Knowing that weight is not fundamental does not make it less real. It makes it part of a larger truth. Humans feel weight because they resist the curvature of space-time. They feel weightlessness when they move with it. They experience different realities because the universe allows multiple perspectives, each consistent, each revealing a facet of the whole. The illusion of weight dissolves, but the truth becomes clearer. Gravity is the silent architecture of the cosmos, and weight is the echo of our resistance to its design. To understand this is to see the universe not through intuition, but through insight. It is to recognize that the world is richer than sensation alone can reveal. And it is to stand at the edge of knowledge with a new awareness of how deeply perspective shapes reality. This is the ending, but not a boundary. It is the moment where understanding replaces assumption, where geometry replaces force, and where the illusion of weight gives way to the profound truth beneath it.